Good afternoon. Welcome to the next video in the Let's Calc series. In this video we're going to focus on the problem set focused on rates of change, which is really just kind of a catch-all title that addresses a bunch of small little pieces that extend our knowledge of differentiation and derivatives. In particular, the focus of this lecture and this lesson and this problem set, therefore, will be on average rates of change and computing them and using them to solve problems. We're going to look at higher order derivatives like the second and third derivative. We're going to look at their applications towards velocity and acceleration, as well as jerk, snap, crackle, and pop if you want to go even further. And then finally, we will look at using the graphing calculator to calculate derivatives for functions we don't have differentiation tools for just yet, or that might just be really hard even if we had them. So without further ado, let's jump into the first question. Our first topic, our first question that we're going to look and address today is coming from the first section of the assignment, which asks you to simply compute the average rate of change for each function over the specified interval and to show any computations. So in this section, your job is to use that difference quotient that gives us what we used to call the secant line slope, or just plain old the slope. It's not going to give us the derivative, but it'll give us a good approximation for the derivative over that particular interval. So from here, where we start in question number 2, I didn't start with number 1 because it was a much more straightforward problem. But looking at number 2 features a little bit of challenge because g of x is equal to 2 cosine of x plus 4 of x. So we have a trig portion and a polynomial or linear portion. And we're on the interval from pi over 4 to 3 pi over 4. My thought in choosing this problem was just that it was going to be a little more intense as far as arithmetic and algebra as you work your way through it, and you have to know a little bit of trig. So it felt like a good opportunity to talk about that a little bit. So let's jump in. So first, we want the average rate of change over this particular interval. So more than anything else, a good place to start is to look at our interval, which in our case is pi over 4 to 3 pi over 4, and to set up the difference quotient we're looking for. So we typically call that g of b minus g of a over b minus a. But in particular, in our case here, this is going to be g of 3 pi over 4 minus g of pi over 4, all divided by 3 pi over 4 minus pi over 4. So we start there just to make sure we know what ingredients and what pieces we're going to have to look for here. In particular, all we need to do is figure out the value of g at 2 particular points, and then we'll be able to just compute what this value is equal to. And although we don't need to simplify, I'm going to attempt to simplify this as much as possible. We'll see if we get there. So let's see. So a couple different pieces here. First, I'm going to go off to the side. This is just kind of a tip. I'm going to go off to the side and compute what g of 3 pi over 4 is first. And then afterwards I'll do the same with g of pi over 4. So in here, if I plug in directly, that's going to give me 2... why am I doing that? We don't need to do that. Let's just put it with all the work. I'll do this more authentically. So g of x, or g of 3 pi over 4, is going to be 2 cosine of 3 pi over 4 plus 4 times 3 pi over 4. And I like that second part because the 4s are going to divide away. So it's a nice little starting point. Next, we need to subtract g of pi over 4, which is going to be 2 cosine of pi over 4 plus 4 times pi over 4. And once again, thanks for playing, the 4's divide out. All this is going to be divided by 2 pi over 4. And of course, we can simplify that, but for the moment, we'll hold off for just a second. Okay, so next, what do we want to do? I want to start cleaning this up a little bit. So I need to figure out what cosine of 3 pi over 4 and cosine of pi over 4 is. Well, in here, I happen to know that the cosine of pi over 4 is right there. It's a 45-degree reference angle. It means it goes 1 root 2. So the cosine of 45 degrees, also known as pi over 4, is just known as root 2 over 2. On the other hand, 3 pi over 4 isn't in quadrant 1, but in quadrant 2, but the ratios are exactly the same. So in this case, if we go to calculate it, we'll get that cosine of 3 pi over 4 is equal to negative root 2 over 2. So basically, we'll have a negative version and a positive version. Let me also point out for a moment that although we don't expect you to simplify, in this case, a final answer can't contain expressions like cosine of pi over 4 or cosine of 3 pi over 4, because those are what we'd call unevaluated functions. We need to evaluate all functions and make sure that we have the correct value, the correct numeric value. That arithmetic is part of what we're aiming for here. So with that in mind, let's go attack a little bit. I'm going to move back to the side. So we said the first part is going to be 2 cosine of 3 pi over 4, which we said was negative root 2 over 2, plus 3 pi. Then the next one, I'm going to distribute the negative sign in as well. Actually, I'll do that in one more step. We'll have 2 times root 2 over 2, and then it looks like plus pi. All this is going to be over pi over 2 by simplifying. So ingredients here, a couple nice things. The 2's divide out. We're going to get negative root 2 plus 3 pi. Here distributing in, we're going to get minus root 2 as well, and then minus pi, all over pi over 2. And then cleaning up that numerator just a little bit, we're going to get 2 pi minus 2 root 2, all over pi over 2. So this is a pretty nice final answer, but personally I don't like the pi over 2 down there, even though this would be fully acceptable. So I just want to clean this up a little bit. So I'll go back to one of our old favorite friends. We are dividing by a fraction, which is the same as multiplying by its reciprocal. So if we distribute everything in, we're going to get 4 pi minus 4 root 2 all over pi. And that's perfectly good, but I don't like the fact that there's that pi there and down here. So I'm going to separate this into 2 pieces. 4 root 2 over pi. We're going to get the answer I'm going to call my final one, which is 4 minus 4 root 2 over pi. And that, of course, gives us the average rate of change of this function g of x on that interval. In other words, it also gives us the slope of the secant line through the 2 points at pi over 4 and 3 pi over 4 on that graph. So again, not a particularly difficult thing to ask you to do. Average rate of change is pretty simple, y2 minus y1 over x2 minus x1, or f of b minus f of a over b minus a, but the arithmetic here was a little more challenging, so we took it carefully. Okay, next, we're going to move on to the next section, which asks you to compute each higher order derivative, which means we want you to compute not just the first derivative, or the slope function, but the slope function of the slope function, or maybe even the slope function of the slope function, also known as the third derivative. So in this case, there's 2 pieces here. The first thing to note is that they tell us which derivative we want based on this first piece in this question. So this one says d3y over dx cubed. That's the same thing as saying they want the third derivative. Second, they gives us the function that we want to compute that particular derivative for. So in here, in order to get to the third derivative, there is no way to go except simply going from the function to the first derivative to the second, and second derivative to the third derivative. We're just stuck that way. We have to do it. So to start with, I'm going to put this into a better position just to see what we have. So I'm going to rewrite it as x to a power, so it's easier to differentiate. 9x squared is pretty good, and 14 is as 14 as possible. We want the third derivative, so we're going to look for y prime next. I'll remind you, though, that notationally, that's the same thing as asking dy dx, or delta y over delta x, the same kind of idea. So in here, we're going to take the derivative of y. That's going to give me negative 5x to the negative 6 plus 18x plus 0. So cleaning it up just a little bit, we get negative 5x to the negative 6 plus 18x. That was the first derivative. We want the third. So let's compute the second derivative, which we could call, keeping this notation the same, d2y over dx squared. Could also call it y double prime. From here, we want to take the derivative of this guy. That's going to be negative 5 times negative 6 when it comes down is 30x to the negative 7 plus 18. And then finally, we were supposed to find the third derivative, so we're going to take the derivative one more time. And notice none of these derivatives are particularly difficult. We just have to keep track of them and, of course, do all the intermediate derivatives. So that third derivative is the same thing as y triple prime. That's going to be 30 times negative 7. I'll be careful here. 30 times negative 7, x to the negative 8 plus 0. Simplifying a little bit, we get negative 210 x to the negative 8. Or the expression, or the way I'd love it to look, negative 210 over x to the 8th. And voila, there is our average rate of change, there is our third derivative that we are looking for. One thing to remember is that there's no fast way, there's no shortcut. You just have to go through all the intermediate derivatives to get there. Okay, next that brings us to question number 8. Question number 8 is as close to a plus question as you're going to get on one of these problem sets. There's no way around it. It just is a challenge on itself. And I still think this is a good one to look at. It's a good challenging question to think about. So we're supposed to compute the 42nd derivative, of y equals 2 cosine of x plus 3f of x minus 10. By the way, hopefully you're amused by the fact that I'm complaining about the question even though I just wrote the question less than 12 hours ago. Go figure. So, if we want the 42nd derivative, the only way to get there would be to go through every single derivative. Maybe. Let's see. So first, if that's y y prime is going to be 2 times the derivative of cosine, which is negative sine, so negative 2 sine of x, plus 3f prime of x plus 0. Y double prime is going to be negative 2 times the derivative of sine, which is cosine, plus 3f double prime of x. Y triple prime is going to be negative 2 times the derivative of cosine, which is negative 2 times negative sine, which is positive 2 sine of x, plus 3f triple prime of x. And then we have the fourth derivative, if only that were where we were stopping. We're going to have 2 cosine of x plus 3f quadruple prime of x. Now, one way to do this problem is to simply continue doing every single derivative up to the 42nd one. But I'd like to think that we could instead find a pattern here and to start to work through it. Before I get there, I am going to do one more derivative just to kind of illustrate my point. Derivative of cosine is negative sine, so that means we get negative 2 sine of x plus 3f to the 5th order derivative of x. So the reason I bring this up is I want to point out that the pattern here has 2 different parts. There's like 2 different columns of the pattern. So if we want to eventually figure out the 42nd derivative of this function, we're going to have to deal with what happens with the cosine term. But then the second part's going to be easy. The second derivative of y gave us 3f second derivative of f. Y triple prime, 3f triple prime. Fourth derivative, 3 times the fourth derivative of f. So I feel confident that this second term here is going to be 3 times the 42nd derivative of x. Or the 3 times the 42nd derivative of f of x. So I feel that's pretty safe. I think the bigger challenge, and in fact I know the bigger challenge, is going to be figuring out what goes right here. So let's try to figure out anything we can from this pattern. So let's see first, like we know sine and cosine kind of oscillate. So let's see first what we get. So on y prime, the first derivative we have sine, double prime cosine, triple prime sine, fourth derivative cosine, fifth derivative sine. What that looks to me is that y and an odd derivative leads us to have, let's see, every single time it looks like for odds we have sine, something sine. And that means for all the evens, since that's always one derivative past or before, we're going to get everything in terms of cosine. And in fact, more than that, for each of these, the coefficient is always 2. So for each of these guys, we're going to have 2 sine and 2 cosine. So since 42 is even, I'm thinking this term is going to be 2 cosine of x. Unfortunately, though, that really leaves us one part of this problem for us to hit. We still have one issue. Is this a plus or is it a minus? And that pattern's a little funkier. We have y prime is negative, y double prime is negative, y triple prime is positive, fourth derivative is positive. So it looks like it goes negative, negative, positive, positive, then it becomes negative again and cycles back through. This derivative is what we would call periodic. You continue, or higher order derivatives in this case have a period. So in here, in order to determine what's happening plus or minus, I want to think about that period or that length of time it takes to repeat or start that sine pattern again. So in particular, what I notice is when I look at the derivatives 1, 2, 3, 4, so I'll go the nth derivative here, and n equals. So basically we're going to be doing values of that, and then we're going to be looking at here. Okay, I just want to clean that up a little bit. So this is a difficult one to explain. So this is n values. Up here we want the nth derivative. We want the sine of it. So in here what I see is for the first and second derivatives we have pluses. For the third and fourth we have minuses before the pattern repeats again. So in a sense 1 through 4 gets plus, plus, minus, minus. If we go 5, 6, 7, 8, they would follow that pattern. 9, 10, 11, 12. And of course this pattern continues onward from there, but I don't want to have to do that many individual steps, so instead let's just fast forward. So looking at multiples of 4, since that's the one thing I see about the end part here, is that we go 4, 8, 12. I know that eventually there's going to be one that features a 40. So in fact that row would have to be 37, 38, 39, 40. That means the next row would start with 41, 42. So what that tells me is that 42 is going to belong to the column right here, and it looks like 42 will therefore be positive. So a pretty awesome thing to look at. Looks pretty good. Except I made an error, didn't I? Oh man, made a big error. And let's see what that error was. I said plus, plus, minus, minus, but just literally look at the picture. It literally goes minus, minus, plus, plus. Like literally the minus signs are right there. Why didn't you stop me? You're using your time machine to reach back into July 8th, 2019 to tell me. So in any event, the structure and the idea was right, just not the execution. So what I see is that the 42nd derivative behaves just like the 2nd, the 6th, the 10th, the 38th, and the 42nd. These are all, I believe, mod 2, or these are all equivalent to 2 mod 4 if you're into modular arithmetic. If you don't know what that means, don't do anything. It's fine. You don't need to. But what I see then is that the sign should be the same, so we should have a minus sign. And so after all that work, the 42nd derivative should be equal to minus 2 cosine of x plus 3 times the 42nd derivative of f. Or if you want, just because it's kind of annoying to have that minus sign in front, you could have the 42nd derivative of f of x times 3 minus 2 cosine of x. And again, that's a ton of work to get there. Like I said, this is probably more of a plus question than anything else, but I think it's a good thing to get used to this kind of idea of looking for patterns and trying to develop some stuff, even when you're not sure exactly what's happening. So really hard question number 8, but you're welcome for the extra challenge and the extra thinking. Okay, that brings us then to question number 9. Question number 9 comes from the section asking you to use those simple applications of higher order derivatives that we looked at earlier involving position, velocity, and acceleration. Some basic physics stuff. So in this section, they ask us to compute the velocity and acceleration functions for each position function below. So the implication is, of course, that we are starting with a position function. And that position function is pretty simple looking. Looks like it should be pretty easy to work with. 4t to the 4th minus sine of t plus 8. So there's our position function. Now, as far as details, hopefully what you'll remember is that if you have a position function, p of t, then the derivative of that position function is just like asking for its rate of change. Like the rate of change of your position is how fast you're moving, as well as the direction, which means that this would be called velocity. So in other words, p prime of t, if p is our position, is equal to the velocity of t, which we're going to call v of t. Third, if we want to talk about the rate of change of that rate of change, you could think of it as the second derivative of the position. You could also think of it as the derivative of the velocity. And that typically gets the name acceleration. Acceleration, which we could call p double prime or v prime. Often we just call a of t. Now it's worth pointing out that you shouldn't use those names, v of t and a of t, without formally defining them with respect to your position function. So if you forget that on an exam, you could lose points. Probably will lose points, especially in a free response context. So keep that in mind. So in here, what are we going to do? Well, we have position. We want to find velocity. So to get the velocity, we need to remember that's the rate of change of the position, which means we're looking for s prime of t. We're just going to call it v of t. In our case, that's going to be the derivative with respect to t of 4t to the 4th minus sine of t plus 8. So none of these terms are particularly hard to differentiate. 4 times 4t cubed is going to be 16t cubed. Derivative of negative sine is negative cosine. And the derivative of 8 is 0. So there is what we're going to call our velocity. So not particularly difficult to differentiate. You just have to be comfortable with the application to attack. Now third, that brings us to the acceleration. So the acceleration is typically defined as the rate of change of your velocity. So how fast your rate of change is changing. The rate of change of your rate of change. We could also think of it as the higher order derivative, because technically if it's the derivative of velocity, it's the same thing as the second derivative of position. For our purposes, that means we're just going to differentiate with respect to t, the velocity, which was 16t cubed, minus cosine of t. So for us to get to work here, and I should probably define that as a of t. Again, can't take that for granted. A of t is going to be 16 times 3 is 48 t squared. The derivative of cosine is negative sine, so this will be minus a negative sign, which makes it a plus sine of t. And there we found both our velocity and our acceleration. Now, one last thing, there's no talk of units on here, but if you're a unit person, you want to think about what those units might be. Let's say that the position was given in feet, like you've displaced yourself or you've moved 15 feet to the right. Velocity would be in feet per time unit, which maybe we'd go with feet per second. And then, of course, acceleration would be feet per second squared. So those could be potential units for what's there. So just something to kind of throw in the back of your head. Nice to see. Excuse me. Okay, that brings us to question 11. 11 is a more traditional application question involving position, velocity, and acceleration. I'm only going to do questions 11a and 11b here. I think 11c is pretty simple, especially with a polynomial for p of t. So if that's an issue, too bad, I guess. Whatever. So in 11, a particle moves along the x-axis. I'll use my most epic narrating voice because it's not very epic. For 0 to 6 time, the position of the particle at time t is given by the equation p of t equals t cubed minus 6t squared plus 9t plus 3. And with that said, we're asked to find the velocity v of t for the particle from 0 to 6. Now that 0 to 6 can throw people at first, but keep in mind it's the exact same 0 to 6 they told us at the beginning, so nothing's really changing here. Remember though, if we want to find the velocity v of t, we need to take the derivative of the position function, which in our case means we need to differentiate t cubed minus 6t squared plus 9t plus 3. It's not going to be hard. V of t is going to be 3t squared minus 6 times 2t, which is going to be 12t, plus 9 plus 0. So there is our velocity function. I will point out that that velocity function, though, is only valid for times between 0 and 6, so we might as well write it down there. But, you know, I'd be looking for the function, of course. Okay, next that brings us to B, the real question that motivated me to do part A. It asks, was the particle moving to the left or the right at time t equals 4? Justify your answer. So this can throw people a little bit when you think about it for the first time, because we're not used to motion in this way that we're talking about here, where we're going literally side by side like that. We're used to motion where the particle is kind of running all over the place, visiting itself. So instead here, we got to be a little more careful. What we're looking for is to look at the sign, SIGN, of the velocity. If the velocity is positive, since we're moving along the x-axis, we'd be moving in the positive direction, which would mean we were moving to the right. On the flip side, if we have velocity negative, or negative velocity, then we'll be moving to the left, because negative velocity tells us we're moving towards the negative numbers. So that's what we're basically using to do this, and it's how we're going to justify our answer as well, is by using the sign. So if we want to find out was the particle moving left or right at time t equals 4, we need to calculate v of 4. Plugging in here, we'll have 3 times 4 squared, minus 12 times 4 plus 9. It's going to be 48. Minus 48 plus 9. Ooh, it's equal to 9. So what I'm seeing is that 9 is greater than 0. So what that tells me is that the particle, look at that little particle, it's moving. So it's according to this, the particle is moving to the right. To the right, to the right, to the right. There's a song saying things. Particle is moving to the right. And then to justify, our reasoning would be because, and I should even say right at t equals 4, be as specific as possible. And the reason is because v of 4 is greater than 0, or you could say v of 4 is positive. Boom. And so there is our stuff, something helpful to keep in mind. Now, because I have a little bit more time here in these videos than you do in class, let's pull up Desmos really fast. And let's take a look at what's really happening here. I think sometimes this is helpful. Now, the way I'm going to graph this on Desmos might not be the most rewarding. It might not add the most to your stuff, but bear with me for the moment because it's going to do a nice job. So it says we're moving along the x-axis, which means there's no vertical movement whatsoever with this guy. So it was t cubed minus 6t squared, 6t squared, plus 9t plus 3. I need to go check this really fast. I don't think I have this right. Minus 6t squared plus 9t plus 3. Oh, cool. So we're going to go that way, and then we're going to have it have position 0. Okay, so now for the moment, this ain't doing the trick. Let me make some changes here. Okay, got it. Okay, so again, ignore the process through which I'm doing this. I just want you to look at the actual image itself. Let's go to 10, and let's go steps 0.001. Okay, so right here, there is our particle. Now let's label this the particle. Maybe that'll help. Hopefully you can see that. Let's change the color so you can make it a little bit better. Nice Franklin purple, black. There we go, that's even cleaner. Done. Okay, so what's going to happen here is our particle is going to be moving as k goes forward. And it's going to go really fast, so hold on. There we go. Okay, so although in our problem they're giving us this function, which we're treating like a function like this for positive and negative, here's what the particle's motion actually looks like. At first it's moving to the right, then notice it stops. Now it starts moving to the left. Remember, we were interested in what was happening at t equals 4, so it slowed down. Now it's moving to the right. And it was definitely moving. At t equals 4, here we go. Here's t equals 4. It's definitely moving to the right. So it looks like we've done a good job of getting that in there. We found what we needed. We confirmed that this was, in fact, accurate. So interesting enough. And again, you can find the acceleration pretty easily on your own. Okay, that brings us next to question 14. 14 brings back in the definition of the derivative, which is good because you should not lose sight of it. But in addition, it also asks you kind of an interesting question. It gives you a difficult task to actually model. We're supposed to evaluate the limit as h goes to 0 of the quantity f double prime of 2 plus h minus f double prime of 2 all over h. So in a sense, we are obviously using a derivative definition. We just got to figure out what it is that's being differentiated, and then how can we represent that very thing. So a couple things in here. First and foremost, what this makes me think about is this expression. The limit as h goes to 0 of f of x plus h minus f of x all over h. So that's what I'm thinking. And we know that that is traditionally equal to f prime of x. There's one extra wrinkle in here, though. Look over at this expression. Do you notice that there's no x in there at all? There's not a single x. That's because the x has had its place taken by the 2. So basically this used to be an x, but we're replacing it with a 2, which means in a sense no longer will our difference quotient have x plus h, but it'll have 2 plus h. No longer will it have f of x, but it'll have f of 2. And that means we won't be actually calculating just plain old f prime of x, we'll be calculating f prime of 2. So our job is to figure out what function is being differentiated over here so that we can then plug in 2 to that particular function. So now as far as locating what's being differentiated, the f of x came at the end, so once again we can see our clearest picture at the end. So looking in here, what it appears we're differentiating is y equals f double prime of x. And again, it's not a 2 because the 2's been plugged in there. The function itself that is changing would be of x. So if that's our function being differentiated, we have to ask ourselves, what is the derivative of that expression? So we need to take the derivative of f double prime of x. Now I hope you realize that's not actually difficult. We don't know what f of x is, we don't know what f double prime of x is, but we know the derivative of f double prime is f triple prime. And what that means then is that this is the derivative that would be coming out of here if we just had x's in it. Since we don't, we're one step away from our final answer. What we need is to plug in x equals 2. And from there, that means our answer will be f triple prime of 2. And now I admit this is a weird question. This is the hardest way I could ask this question, but it's important to recognize that no matter what type of function goes in there, you're differentiating the one that's being subtracted and computing a particular derivative, which again goes faster because we know how to differentiate so well. So there you go. There's 14. Okay, we're going to jump into our next question, which comes from the calculator portion of the assignment, to ask you to compute some derivatives using your graphing calculator. So in this case, I'm going to show you two separate ways to do it, each of them equally effective, just kind of depends on your preference, although I definitely have one. And I'll be using the TI-84 graphing calculator simulator, or emulator, straight from Texas Instruments, or at least the free trial version, because I have not sprung for the full one yet. So in looking up here, of course, the difficulty here, the need. Why do we need to use a graphing calculator? Why would we need that? Well, the reason, of course, is that this function has lots of, I always call it frou-frou. There's just a lot of stuff going on here. We have x times another function, so we have a product of two complex functions, One of those functions, sine inverse, we didn't even know how to differentiate. Then we have x squared over 33, which is just messier again. This is just a really messy function. So it's one we don't necessarily want to have to mess with, even if we had the tools for it. And truthfully, for now, you don't have those tools. So what we want to do instead is we want to ask something more powerful, which is our graphing calculator. So let's go look at our graphing calculator here. Here it is. We want to do this one of two ways. So the first way is to use the graphing calculator's graphing ability, to literally graph it and find the derivative there, through that second trace menu. So in here, what I'm going to do is I'm going to clear all the work that we've done before. Clear. We want to input this function, which is x times sine inverse of, let's see, math, fraction, x squared over 33. So as ugly as can be. Next, we're looking at f of 4, so the standard zoom should work out nicely. So let's graph our function. So there it is. Notice the function just kind of seems to stop. Now it's possible it is asymptotic and we're just not sure, but it looks like it really stops. What we're interested in is in what's happening at x equals 4. So now in here, if I just trace and go to x equals 4, I get the x and y coordinates, but that's not what we're asked for here. We're supposed to find the derivative. We want to know what the slope is along there. And looking at that picture, I feel confident, hopefully if you can see my mouse, see it tracing, I feel confident it's going to be a positive number, just not sure what it is. So to get there, I'm going to use the second trace button. It takes us into the Whittler menu. Looking down, the one that describes slope is the one that says dy dx. Literally, that's just another way to describe the slope. Now, and by the way, this won't find us the derivative function. Only fancy calculators and Wolfram Alpha can do that for us. What it can do is it can calculate the derivative at a point and tell us the slope at that specific point. So I'm going to choose option 6. I'm going to now plug in x equals 4 and press enter. And this will tell us our slope. So this value right there is our slope, 1.615. So f prime of 4 is approximately 1.615. Now, as a heads up, just because this is as good a time as I need to talk about it, 1.615 is accurate to 3 decimal places. It's rounded to the nearest thousandth. But there's actually another answer that would be acceptable for this problem, not just among me and the teachers at school, but also on the AP exam, where you have to be accurate to 3 decimal places. The other option would be to round it, or excuse me, not to round it, but to truncate the answer to 3 decimal places, in which case we would cut off after the thousandths place and just record what was there. So we could also report this as 1.614. Both answers would be equally acceptable. No reason either of them could go wrong. So there is our answer using the graphing method. But there is another method. So I'm going to quit this area. Now recall, y1 is already graphed in and put our function in. I don't want to have to put it in again, but theoretically we could. What I want to point out is that we have another option here, which you may have run into if you've done the calculator or the standard quiz model already. But notice in this menu, the math menu, again that's right there, the math button, right under alpha, the math menu features nderiv parenthesis. That is giving us the opportunity to calculate a derivative. So for us here, we get the derivative. It has 3 things to fill in. It has dd blank of blank evaluated at blank equals blank. So there's a lot of blanks to fill in here. The first one, though, is the variable. I'm going to choose x. Notice that as soon as I choose x, it fills in the x over there because we're going to evaluate this at a particular x value. Now to do this, one way that we could do this is we could use the fact that we already input the y or the function value, the function as y1. We could go alpha trace and choose y1, and then that would calculate our slope for us. And last but not least, we would need to put in 4 to evaluate the slope at 4. When we do, we get the exact same 1.6149 that we got before. Alternatively, if you did not put everything into the graphing calculator or into the y features, you could of course plug in everything like normal, and you could just type in the function itself. X times arcsine of x squared divided by 33, close parenthesis, and we get our same answer. So it doesn't matter how you approach it, you get to the same place regardless of what you do. So there is how you can use your graphing calculator to evaluate a derivative and define that derivative at a point, maybe even write the equation of a tangent line that way. Okay, finally, this brings us to our last question, which is kind of a word problem style. You will see some of this on your exam for this unit, and you'll definitely see harder versions of this on the AP exam when we get there. But of course, there's so much more calculus to go. Don't get too excited about that. So in question 18, we are told that a bug is moving along the y-axis. So we're not sure why. We're not sure why it's so locked into going do, 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 do. But it is. And it says that's happening for times 0 to 8. And its velocity is given by y of t equals that thing. So before I do anything else, I find it very relevant and very important to note that they are telling us the velocity of this function, not the position. So truthfully, we don't know anything about the position of this function right now, and we won't until term 3, or 4 if you're in term 2. So basically what we're given is velocity. So that means we will be using the graphing calculator to evaluate the velocity, or we could use the calculator to differentiate and find the derivative of velocity, also known as acceleration, at a particular point. So let's see what the question asks us to do. So first it's asked, what was the bug's velocity at t equals 4? Well, since the velocity is given by y of t, what we want to calculate here is y of 4. So we want to know what y of 4 is equal to. So in here, we can actually find y of 4. We could literally find the value of y of 4 by plugging 4 into our function. So there's our function. Go with the cube root of the ln of 4 squared plus sine of 4. So if you wanted an exact value, well, then there it is. I don't want an exact value. I'd rather let the calculator tell me. So in here, we're going to do a couple things. First, we're going to set something up. So I'm going to remove that function we just graphed from question 15, and I'm going to put in the new one here. So by the way, if you have a cube root button, it should be in the math menu. If you don't, though, let me remind you really quickly that this is the same thing as the ln of t squared plus sine to the 1/3 power. So however your calculator cooperates, you choose your method. For me, I'm going to choose the cube root button because it's there. On the inside, as we said, we're going to have natural log of t squared. Again, even though it's t in the problem, I can replace that with an x for our purposes here. We'll graph the relationship the same way. Okay, now I have y1 in my calculator as that cube root function, the velocity that we're looking for. So a couple different ways to evaluate this. So once again, zoom 6, we could graph this function, and we could find the value at 4 by tracing and typing in 4. When we do, we get that x equals 4, so t equals 4 implies y equals 1.397. So that is first option, and of course we could truncate as well, so 1.396. Either option is just fine. So that is one way to get that value. Another way, which actually I find to be really simple because it doesn't require us to graph anything or wait for a graph, is we could once again use that notation of y1 being our function in question. We could go alpha calc and select y1 and do y1 of 4. And this will tell the calculator to plug in 4 to the function y1. And look at that, we get the same 1.396 or 7 that we would have gotten otherwise. So to get the velocity, of course, there's a little bit of reading comprehension involved as well. You did have to recognize that you were told the velocity as opposed to having to differentiate to get it. Once you have it, you've got a plethora of options for plugging into in the calculator. Okay, next that brings us to part B. Part B tells us, directs us, find the one time from 0 to 8 for which the bug was at rest. So now, I don't know much about the nocturnal habits of bugs. I'm not even sure if bugs are nocturnal. I don't know much about them. I just hope that they stay outside of my house. But in this particular case, we want to know when the bug was at rest. So when did the bug stop moving? So in that phrase that I just put in there might not be something that you know of. You don't necessarily think about it this way. But at rest does not mean they pulled out their pillow and blankie and they decided to take a nappy nap. It means that you're at rest if you're not moving. And let's think about this in more precise mathematical terms. Not moving. Here, I'll just do this right. If you're not moving, that's the same thing as saying that your velocity is 0. So what we're looking for in this particular case is we want to figure out when is y of t equal to 0 for t values between 0 and 8. So this is one where you could, of course, attempt to solve this equation. It is possible you could try to solve this equation by hand. But as a warning, eventually you'd end up having to solve t squared plus sine of t equals 1, I believe. And that's, I don't think you want to do that. So instead, let's go to our graphing calculator. Our graphing calculator knows how to solve equations, in particular ones that are equal to 0, since that would just be a literal 0. So let's see. Our graphing calculator is right here. We're going to go into the y equals. Now our function's already in there, so we're ready to graph it. Now I do see that there are two different zeros, but we're interested in the one between 0 and 8. So I want to try to figure out what's happening somewhere over here. So in fact, looking at this, it looks like our answer is going to be somewhere less than 1, between 0 and 1. So to make this work though, let's see. So I'm going to do second trace. I'm going to calculate the 0. I go enter, enter, and I'm going to guess it's at 0.8. Just could guess whatever. Okay, and it tells us that the one place where the velocity function is equal to 0, at least for times between 0 and 8, is 0.637. Or, of course, the truncated version, 0.636. And again, hopefully you've already caught the fact that there are no units in this problem, so we're not having to report units. We don't have to say time units. Just don't mention anything. If there are units required for a particular question or answer, it will say include units. This does not, hence no units included. Answer, though, we found. The big thing to pull out of that, though, is to remember that something's at rest. It means the velocity is 0. It's an important thing that's going to come up a bunch as you move forward. Okay, third, that brings us to question 18C. What was the bug's acceleration at t equals 4? Well, what we know about acceleration is that it is the rate of change. It is the rate of change of the velocity. It's how fast your velocity is changing. So it's measured in things like feet per second, because it's how much your velocity increases or decreases, or the rate at which your velocity is increasing or decreasing. So in looking here, if we call acceleration a of t, we know that a of t is going to be equal to v prime of t. And in our particular case, since we were given since we were given the velocity as y of t, a of t is going to equal y prime of t. And we're specifically interested in what's happening at 4, which means that we want a of 4, which is going to be y prime of 4. In other words, we want the slope of our function at t equals 4, because that will translate in the context of this question into being the acceleration of our bug's velocity, the bug's motion. We'll go with that. So in here to get there, we need our graphing calculator, of course. Probably going to block some of this stuff. Let's move it over a little bit. We should have room still. So looking in here, we want to find the derivative at 4. Now I do already have the calculator drawn up. So of course one option would be to second calc and then find dy dx, which is 6. Then I could tell it to look at the derivative at 4. And it tells me my derivative is 0.082. And that is our acceleration. Now with that in mind, of course, we could go even a little bit further if we had to. I think this is probably about as far as I can go. We could also, of course, use math 8. We could call everything in terms of x. We could go at x equals 4. And we could, of course, use alpha calc, or alpha trace, and plug in y1 and get that same value we had just gotten. And that gets us our answer to C. Okay, finally, the last question asks us, what was the average rate of change of the bug's velocity for times 3 to 6? This, not particularly difficult. It actually would have been a fairly difficult question had we asked for the average rate of change of the bug's of acceleration, because that would have taken us a little bit more time to get there. That would have given us what's called the average jerk, by the way. This instead is going to give us the average acceleration, but technically that's neither here nor there. So in here, though, average rate of change, one of those new vocabulary things we came up with. For a function y, that's going to be y of 6 minus y of 3, all divided by 6 minus 3. And then, of course, what that's equal to, we could evaluate by plugging in 6 and 3 and then doing the division. But again, graphing calculators do a really nice job of this. If we want to put this in, remembering that y is literally in our calculator as y1, we can go in here and we can set up a quick fraction. We're going to do alpha calc, or alpha trace of y1. I want to do y1 of 6 minus alpha trace y1 of 3, all divided by, and I know 6 minus 3 is 3, but for the moment, let's just put it in for clarity. When I put it through, I get 0.075. And there is our answer. And again, I will point out, this does tell us, this calculates what's called the average acceleration. It's also equal to the average rate of change of the velocity. But for the moment, we don't have to know that. It's just a nice little thing to go through. And with that said, I believe that does. It ends our video here. Hopefully this has been helpful and clarified some stuff, given you some extra tips and information, and helped you work through this rates of change problem sets. And again, hopefully you're feeling comfortable with differentiation as well, because tomorrow's lesson is going to be a new differentiation technique. Without further ado, thank you for watching. Have a great day.